Hi, I'm Spring, and this is my Lab 1 video report for Physics 2211. So here's my mini table of contents that I will go through briefly. First, the lab's purpose is measuring the motion of a tennis ball, predicting its motion through a computational model, and comparing the two data sets to draw conclusions about how my system is affected by its surroundings. Here's a brief outline of the organization of my analysis. First, I will discuss Newton's second law, then connect it to both tracker and my GlowScript code. Then I will further analyze the observed versus expected data, as well as answer what-ifs and any assumptions that are made. This lab will focus on connecting Newton's second law, which is sometimes referred to as the momentum principle, to a real-world scenario of a tennis ball rolling at a constant speed. We will do so by constructing a computational model that will predict the motion of the tennis ball given certain dimensions like mass. With the data, you can compare the computational model to your actual data and see how they differ based on assumptions and errors. So the momentum principle here can be derived from Newton's second law with these steps. So after multiplying the first equation by mass, rearranging allows us to get momentum, and more specifically, final momentum, on one side. However, because our case involves constant velocity, we assume momentum is constant and force is zero. Under conditions with no friction, objects that stay at rest will remain at rest, and objects in motion will stay in motion, because there's no net force acting on it. In this lab, I will assume there's no net force acting on the tennis ball. Here's my video and tracker of the tennis ball rolling, and I measured it within this time frame, and then it records the data on the right-hand side of the time and then X position. So here's my GlowScript code. And then when we run the program, you can see that it looks pretty similar to the tracker video shown. And then I'd like to discuss these two chunks of code because they are key to the principles of Newton's second law. First, we must have initial position and velocity vectors. These initial conditions account for all past interactions, and all further calculation accuracies are determined by these values. So delta t is also important because predicting future motion is an iterative process that is more accurate with more calculations in the set time frame. If we made delta t larger, our predictions would be less accurate. And then the second set of code shows the iterative process in motion with a while loop. Each 0.01 seconds, the ball velocity and position are updated and then recorded with the assignment statements. And then here's my data with the observed and predicted time and position separated to the left. Not all of my predicted data is shown, but it's illustrated on the orange graph. And although my observed line of best fit is surprisingly linear, there's still error with r squared being 0.99. This may have resulted from human error in tracker and the imperfections of the tennis ball in the concrete it rolled across. And as expected, the predicted position and time graph is perfectly linear. The initial velocity should stay constant as a result of having a net force of zero, which is shown in the orange graph having a slope of negative 0.399, which is what we got in tracker. However, the observed graph in blue does not have a constant velocity because the data points don't fit that straight line. And then when we combine the graphs, it reveals the errors of the observed data set. So as I plotted the points on tracker, I noticed that around halfway through the frames, the tennis ball begins to travel off from the intended line, and it's reflected in the curvature of the blue observed line. However, the lines are still quite similar in the beginning, which is to be expected. So, what if I decided to set my axes as something different than plus x in the right direction and plus y in the upwards direction? If I flipped the x-coordinate system, my results would probably be the same numerically, but the values would be positive instead. The code would reflect these changes as a result by having a positive initial position and velocity. But since there's no angles or analysis of the y-component, changing my coordinate system by just flipping it doesn't complicate my results or analysis. And then what does it mean? My computational model effectively predicted the motion of the tennis ball with a net force of zero. So we're unable to say how many pushes or pulls are in the system. So truly there's no scenario with the systems we encounter in everyday life with no friction.